TM361, the Mariner 9 spacecraft arriving to be launched to go into orbit around Mars and map it systematically. There'd been 3 previous flights to Mars, flyby missions. They'd seen moon-like craters as they zipped past, taking their strips of photographs. There were suggestions Mariner 9 should be cancelled. The answer was already known. Mars had craters. What was the point of looking at another moon? But they did go. A member of the TV team was Bruce Murray.
As it turned out, Mariner 9 proved to be an extraordinary exploration mission. I think it was the most astounding mission perhaps the United States has flown to date in many ways because of the nature of the discoveries that were found. There's been a profound and I think irreversible cultural change brought about by the very act of space exploration and by having it well photographed. It means that the photographs could speak for themselves, not be interpreted through the jargon of science.
Well, the whole of the Mariner 9 mission is quite fascinating. The particular part we're going to look at today is the story of how these remarkable photographs were got back to Earth. To appreciate just how remarkable these photographs are, we should realize that at the time, Mars was 84 million miles away from Earth, and yet the transmitter had a power of only 20 watts. You can contrast this with the Crystal Palace transmitter, which serves an area of about 60 miles radius, and yet has a power of 40,000 watts. Well, the way in which this feat was accomplished of getting these remarkable pictures relies upon error-correcting codes. But before we can get into that, let's look at the whole system of the transmission in some detail. If you magnify a picture like this, you can see it's built up from a regular array. In fact, there are 500,000 of these tiny picture elements in one frame, and each one is generated on board Mariner 9. Now, each element you can see has got a uniform shade of grey, and there are varying shades present. For example, if we look at this particular element, Mariner 9 would represent this by this digital sequence. Now, why have we got 9 bits here? Well, the reason is that the Mariner 9 cameras were so sensitive that they could record no less than 512 distinct levels of grey. And that's just what we get from 9 binary digits. So with 9 bits for each picture element and with more than 500,000 elements to each picture, it means that one frame is represented by something like 5.25 million bits. Now, these somehow have to be transmitted to Earth in some form or other, and there they, at the Earth station in Pasadena, reconstituted to get all the grey little squares again and put the whole thing back into a picture. Now, as I've said, somewhere in the middle of all this is the subject of error-correcting codes. And the person who knows all about coding theory is Professor van Lint from the University of Eindhoven.
As Roy said earlier, a problem arose because of the low transmitter power and the vast distance separating Mariner from Earth. 20 watts over 84 million miles. Now, 20 watts is about the power of a car brake light. Imagine trying to see that all the way from Mars. The weak signal really presents a problem. If we were to point an antenna towards Mars and tune in on Mariner 9's channel, we would hear something like this, called noise, generated by a whole host of radio sources in the universe and also partly by our ground-stationed receiving equipment. Now, noise is a fact of life. We can't get rid of it. If we could imagine noise to be absent, Mariner 9's signal would sound something like this in comparison. But in fact, we hear both signals at the same time, and the noise swamps Mariner's signal. Now, the effect of this noise on the zeros and ones, which were mentioned by Roy, is that sometimes a 0 is interpreted as a 1 and vice versa. and the result is that the quality of the pictures deteriorates. In fact, for Mariner 9, the picture's quality would have been completely unacceptable to scientists. So to do something about this noise, the thing that was used is error-correcting codes. Now, what are error-correcting codes? How do they work?
Well, every error-correcting code relies upon the idea of redundancy. And I can show you what redundancy is all about by looking at something which you're already familiar with. This diagram here is in fact the Farnell plane. Well, of course, it looks very strange. You haven't seen it in this form, but nevertheless, it is a representation of the Farnell plane. If you look closely, it's got 7 points numbered from 1 to 7. It's got 7 lines, which we've lettered A, B, C, up to G. And if you look, you'll find every line has precisely 3 points on it. So this is, in fact, a representation of the Farnell plane. Now, the other evening, a friend called, and he left a message for me about this Farnell plane. Let's listen to what he had to say.
Let's look at that problem on the Farnell plane. And the line I want you to look at, Roy, is line 1, 7.
Well, I didn't catch the end of that, so just let's listen to it again.
And the line I want you to look at, Roy, is line 1, 7.
Well, I still didn't get it, but does it matter? Let's look at the picture. He said something about the line 1, 7, and then we missed it. But you see, there is only one line through the 2 points 1 and 7, so what he was trying to say must have been 6. And the reason I can deduce this is because of redundancy. You don't need 3 points to specify a line in the Farnell plane. And that's what redundancy is all about. Now, of course, we want redundancy in some digital code. So obviously we've got to add extra bits in some systematic way. And it just so happens that there's an easy example of this readily to hand.
Now, this is just the incidence matrix of the Farnell plane. For instance, line B contains the points 4, 1, and 5, marked by the 1s. Now, suppose we take these rows as code words in a code. Here you see an example of redundancy, because to represent these 7 different states, I need only 3 binary digits, and I'm using 7. Note further that A and B differ in 1, 2, 3, 4 positions. And the same is true for any pair of words. We say that they have Hamming distance 4. The effect is that if one of these words is transmitted as a message and it is received with 1, 2, or 3 errors, it has not changed into one of the other words. And we see that something is wrong. Now, how about correcting errors? Well, here's a word that is not on our list. Suppose we receive this word as a message, and we have to decide which one of these 7 was transmitted. Now, the received message differs from A in 1, 2, 3, 4, 5 positions. We'll mark that. It differs from B in 3 positions. Differs from C only in the first position. Differs from D in 3 positions, from E in 5, from F in 3, and from G in 5. So if C was actually transmitted, then we have received a word with 1 error. And we will assume that this is what actually happened, because on a reasonable channel, it is more likely that only 1 error occurs than 3 or 5. And the effect is that we correct that error. Now, let's clear the board. Let's put up this word and record the distances to the code words. We now see that there are 3 words with minimum distance to the received word. and we detect that at least 2 errors have been made, but we cannot decide which message was transmitted. Of course, if we have to guess, we would take C, D, or F. We say that the code has corrected 1 error and can detect 2 errors. Now, what about 3 errors? Let me show you that on a much simplified model which I have over here. Now, the dots in this extremely simplified model indicate words which we could take as words in a code. And distance is just the regular distance in the plane. Now, suppose, for instance, we take this as a code word, and maybe this and this. So here we have chosen 3 words as code words. Now, these 4 words all have distance 1 to this code word. And similarly here, and also there. Now, if we were to receive this word as a message, we would assume that this had been sent because it is the closest code word. Now, this point here has distance 2 to this one. It also has distance 2 to this one, and it has distance 2 to that one. So if we receive this message, we see that something very much wrong has happened, but we cannot decide which word was sent. Now, suppose this word is sent, but we actually receive this word. What will we do? We will assume that this was the message which was sent, and we will make a mistake. Now, the code based on the Fano plane, which we discussed a minute ago, is too small to be of practical use. But it is the germ of a whole series of codes which include some very good codes, including the one used by the Mariner.
Well, how'd you like my new wallpaper? It's a very interesting pattern, and like most wallpaper patterns, there's more to it than meets the eye at first glance. This particular pattern is of special interest to us. If you remember, a little while ago, we were looking at the instance matrix of the Fano plane. Something very interesting happens if you try to superimpose that instance matrix on this pattern. Let's put it somewhere down here in the bottom right-hand corner and just watch what happens. Well, can you see that all the zeros are on blue squares and all the ones on yellow? So the color reflects the digital pattern. Now you remember we used the instance matrix of the Fano plane as a code. So we've already seen the pattern of one code embedded in this wallpaper. In fact, there are many more. This in fact is a very important pattern, so I think I should show you just how it can be constructed. What I'm going to do, in fact, is to start off in the top left-hand corner. I'll start off with a single blue square. And then I'm going to do, stage by stage, exactly the same thing. I'm going to reproduce what I've got so far to the right. So in this case, it's just another single blue square, another blue one below. And the gap I'll fill in with the same pattern, but with the colors reversed. Well, I've only got one color, blue, so I get yellow. That's the end of the first stage. I repeat the process. I take the pattern I've got so far, here it is, and I reproduce it to the right and below. And then I fill in the gap with the same pattern with the colors reversed. So here I have 3 yellows instead of 3 blues. That's the end of the next stage. Again, the same thing all over again. I take the pattern I've got so far and I put it down to the right, and the same pattern below, and I fill the gap in with the same pattern with the colors reversed. Well, I could go on like this indefinitely. If I went on just one stage more, I'd get the wallpaper pattern, which is behind me. And if I went on a further 2 stages, 3 stages and all beyond this, I would get a pattern that included within it the pattern of the code used by Mariner 9. But that's just too far for us to jump. Incidentally, what I've actually been doing here, this process, is related to the Hadamard matrices, and the whole structure of repeating the pattern in this way is in fact the notion of a Kronecker product.
We can see another way of building up the pattern, which will show a link to coding theory. Let's start with a row of zeros. Remember, they were blue on the wallpaper. Now we introduce this word. Call it C0. It is simply 0, 1 repeated. If we add this word to the row of zeros, we of course get C0 back again. Now we introduce C1. It is 0, 0, 1, 1 repeated. We shall add this word to the top line to reproduce C1. And now we add it to the second line. So 0 and 0 is 0, 1 and 0 is 1, 0 and 1 is 1, and we're doing addition mod 2, so 1 and 1 is 0, and the addition goes on in that way. We again introduce a new word, C2, which is 4 zeros and 4 ones repeated. Again, we add it to the top row to reproduce C2. We then add it to the second row, addition again, mod 2. We add it to the third row, and we add it to the fourth row. And thus we have obtained 8 rows of our pattern. To continue, we introduce a new word, C3, which is now 8 zeros and 8 ones repeated. Again, we add it to the first row, and then we keep on adding to the second, third, fourth, and so on until we obtain 16 rows. And we can go on in this way to obtain patterns of any size and any length we like. Notice that every row here is obtained from the top row by adding one or more of C0, C1, C2, and so on. So every row here is given by this formula. Now here, for instance, alpha 1 is 1 means that the row C1 is added on, and alpha 1 is 0 means that it is not added on. Now think of alpha 0, alpha 1, etc. as data bits. Then here you see a formula which changes a short sequence of data bits into a long string of zeros and ones. Remember, the blue squares were 0 and the yellow squares 1. And this is the way information is encoded. Now, in practice, it turns out that the right-hand half of this picture is a good code to use. It is known as H3. It consists of 8 letter words, and in the total 16 words. Any two of these words differ in 4 positions. The code used on the Mariner is very similar but larger, and there any 2 words differ in 16 positions. Now let's see how good this rather simple code works in practice.
Well, I've been putting H3 through its paces, and let me try and explain what I've been doing. I have here a computer, and this is able to simulate the whole process for me, the coding process and the transmission. And I've begun by having this picture stored within the computer. Now this picture is made up of something like 53,000 odd elements. They're black and white, and you can see this more clearly if I look at this printout of the picture. You look here, you'll see most of it's white dots, but there's some black dots scattered around. So I'm going to simulate then the transmission of this picture. Well, we can see more clearly, I think, if we look at just a part of it. So here then we have just an 8 by 6 array from somewhere in the picture. Let's look at the digital form of that. And here we have it. You can see that we have a 1 representing each white square and a 0 representing each black square. Well, before we do any more, let's just let the computer simulate transmission without any coding at all, and let's see what happens. Now there's noise, remember, being put into it, and if we look closely, if we're lucky, we can see there's a 0 there where there was a 1 over here, and I think you can see there's a 0 there also where there was 1 over here. So there are errors introduced. If we look what that does to the picture, again, you can see fairly clearly, I think there's a white spot missing there, and also there's a white spot missing there. So errors are introduced. That doesn't look terribly bad, but if we look at a printout of the whole picture, I think you can see how bad it is. The picture is, I think, fairly obviously degraded, and it's particularly obvious if you look at the hat, which was all black before, but look at it now, lots and lots of white spots. Well, what we're going to do now is to see if H3 can do any better. So first of all, let me get rid of this transmission. Before we transmit this time, we're going to code using H3. Now remember, H3 takes 4 bits at a time, so it's going to take those first 4 bits, it's going to code them up as 8 bits. Let's see it happen. There you are, 8 bits came, and for each second of 4 bits, we get 8 bits in the coded form in H3. Now we simulate the transmission once more. There's still noise, so we're still going to get errors in this picture. There's one, look. There's another one at the end. And you can see various errors occurring. But what does H3 actually do with this? Well, let's decode it and find out. Here's the decoded form. Now remember, now we have a degree of error correction. We can correct 1 error. And the easiest way to see what's happened, I think, is to go and look at the picture. There were errors, remember, in transmission. But if you look at this picture, I think you'll find there is, in fact, only 1 error. That's here, where we have a black spot where we had white before. It's particularly good if you look at the thing I started with, which was this picture. This is the complete picture after transmission and decoding by H3. I think it's fairly obviously better than it was before. Just look at the hat again. Not so many white spots. If I compare the two here, this was the old one, you see there's an enormous improvement just using H3. So the situation is certainly very much better. But this is only from H3, which is a very simple code, and will only correct 1 error. H5, the code used by Mariner 9, remember, will correct up to 7 errors and can give a much better performance than this. And it, in fact, can produce fairly remarkable pictures like the ones behind me here. These pictures, indeed, are quite remarkable. Often you say that a picture's worth 1,000 words. Well, if you do the calculation, you'll find out these pictures are worth 873,000 odd words.